Hi, welcome back to our flipped classroom. And today we are talking about electron configuration and what that tells us about the properties of the atoms and the elements and the trends that we can see on the periodic table. So today we're going to be talking about four particular atomic properties. That would be the size of the atoms, which we usually refer to as atomic radius. And then three trends that have to do with reactivity. And those are ionization energy, electron affinity, and electronegativity. So we're going to go through, we'll have a quick review of a few terms, and then we will jump in and define these four properties, and then talk about the trends and how they relate to where the electrons are. So just a quick reminder that we use these two terms, periods and groups or families. And periods are those horizontal rows on the table, and the groups or families are the vertical columns on the table. And both the periods and the groups you've come to understand as we've talked about orbitals and energy levels and suborbitals. We're coming to understand that the periods and the groups are both determined by that electron configuration of the element. So the period is determined by the overall energy level of the valence electrons, those outermost electrons. And the group is determined by the orbital that is being filled, or which electron is going into the orbital of the orbital being filled. So just a quick reminder, again, valence electrons are those electrons in the outermost energy level. They are usually located in the incompletely filled main energy levels. So for our main group elements, that's our S block, and our P block, we're talking about the electrons in the outermost S and P sublevels. And these are important because these are the electrons that are available to be lost or gained or shared when we form chemical compounds. Okay, so let's jump into our definition. So we're going to start with atomic radius because it's pretty much foundational to the other three characteristics. So it's really difficult to measure an atom. And because we know that the electrons are in electron clouds and they can move, it's very, very difficult to measure an individual atom. However, we can, with fairly reasonable accuracy, measure the distance between two bonded atoms. And so we take half of the distance between two covalently bonded diatomic atoms in a molecule as the atomic radius. And so radius is just like we think of it in the math class. It is the distance from the center of the circle to the perimeter of the circle, or the circumference of the circle. It's just that in chemistry, it's hard for us to measure the circle. So we have to measure the distance between two, cut that in half, and call that the radius. So as we go across a period, so we're within a period and we're going across the periodic table, we're adding more stuff to our atoms, and yet radius decreases. So this feels a little bit counterintuitive. So let's take a look at what the electrons are doing and see if we can explain why that's the case. So as we go across a period, we're staying in the same energy level. We're not adding any more shells. We're not adding any more layers. And so the nucleus, as we're adding protons, is gaining in charge. And there's no additional electrons between those outermost, those valence electrons, and the center. And so although we're adding more stuff, we're also increasing attraction because we have more protons and more electrons, and they're being pulled together more. And the way we talk about that is called increased effective nuclear charge. So what that means when we talk about effective nuclear charge, we're talking about the charge of the nucleus, so the number of protons, minus the number of electrons that are in those inner shells. And as we go across a period, the number of electrons in the inner shells, inner energy levels, is not changing, but the number of protons is increasing. And so that attraction is increasing. But as we go down a group, so we're increasing energy levels, we're increasing the number of protons, but we're also increasing the number of core electrons. So we're increasing the number of energy levels. And so As we add shells, as we add energy levels, the radius actually increases. So as we go across a period, radius decreases. The atom actually gets smaller, even though there's more stuff. But as we go down a group, because we're adding those energy levels, we are increasing the radius because that those inner electrons increase shielding that decreases effective nuclear charge. And so we can see that if we actually look at atoms, that as we go across the table, this atomic radius decreases. And as we go down the table, the atomic radius increases. Okay. And this is just a graph of radius as a function of atomic number. And you'll notice that these are elements 1 through 10. It's decreasing. That's because we're going, 3 through 10. We're going across the periodic table and radius is decreasing. But now we drop down a row or up an energy level and the atomic radius jumps up and then we see it decreasing again. So as this is going across and this is going down. This is going across, this is going down. And you notice that when we get into the d orbitals, those transition metals, that there's not a lot of change in atomic radius. So as we go across the transition metals, those d orbitals, there's not a lot of change. So if we were to sum it all up, if we take a look at our periodic table, as we go across the periodic table, atomic radius decreases, the atom gets smaller. As we go down the table, atomic radius increases, the atom gets larger. So that's our first atomic characteristic that we're going to talk about. Now let's move on to the second one. So the second one is called ionization energy. And we know that we have two kinds of ions. We have cations and we have anions. But when we talk about ionization energy, we are specifically talking about the energy that is required to remove an electron from an atom. So we're talking about making cations. It generally tends to increase across a period because as we're going across a period and we're adding those additional protons, the radius is decreasing. So that means those outermost electrons are actually closer to the nucleus and therefore they're harder to remove. So you can think of this kind of the same way you think of bringing two magnets close together. If you have two magnets close together or even touching, they're hard to pull apart. But if they're a little bit away from each other, they're not as difficult to remove. So as our radius gets smaller and the protons and electrons get closer to each other, it becomes more and more difficult to remove electrons. And this is one of the reasons why metals lose electrons fairly easily, but nonmetals don't. As we go down a group, because we're adding those energy levels, because the electrons are getting farther away from the nucleus, they become easier to remove. And so this means as we go down, ionization energy tends to decrease. It takes less energy to take one electron off. And that greater shielding means a decreased effective nuclear charge. So the attraction is also not as strong. So we can summarize this one. So we said as we go across the table, atomic radius decreases, but ionization energy is going to increase, in large part because that atomic radius is decreasing. And as we go down the periodic table, ionization energy is going to decrease. It becomes easier to remove an electron. So we've talked about ionization energy. Let's talk about kind of the flip side of that, which is what we call electron affinity. So electron affinity is defined as the energy that's released when an electron is acquired by a neutral atom. So now we're talking about making anions. And so the amount of energy that is released when that electron is added. So as we go across a period, that electron affinity tends to increase. So more and more and more energy is going to be released when you add an electron. If you try to add an electron to sodium, it's not going to release energy. But if you try to add an electron to chlorine, it is going to release energy. And that's because as the radius decreases, those electrons are getting closer to the bonding atom's nucleus. Again, that attraction gets increased. Electron affinity tends to decrease down a group, or it'll remain the same down a group. And that, again, as the radius increases, those electrons are farther, there's less energy pulling them in, therefore less energy given off when they are pulled in. And this just shows those numbers. You'll notice that the one big exception with electron affinities is that we kind of ignore this, the noble gas family, because the noble gases don't have high electron affinities. They don't form ions easily. They do have ionization energies. They have exceptionally high ionization energies because it requires a lot of energy to pull an electron off of a noble gas. But electron affinity, remember, is the energy released when you add one, and they're not going to release energy when you add one. Okay, so again, summarizing it, as we go across the table, electron affinity is going to increase. As we go down the table, electron affinity is going to decrease. Okay, so our final characteristic that we need to talk about is called electronegativity. And we've talked a little bit about electronegativity. So electronegativity is defined as a measure of the ability of an atom in a chemical compound to attract electrons to itself. So this is how strongly an atom can pull electrons towards itself when it's in a covalent bond, or possibly in an ionic bond. So as we go across a period, as that atomic radius is decreasing, the ability of the protons to pull the electrons in gets stronger and stronger. And so electronegativity increases across a period. And as we go down a group and the electrons are farther and farther away from the nucleus, that electronegativity tends to decrease or remain the same. So we can see our periodic table of electronegativities. Again, like with electron affinity, we've ignored the noble gases. You'll notice they're not even on this table. We do have values for everything. Fluorine was assigned an electronegativity value of 4, and everything else is assigned relative to fluorine. And so we can see that fluorine is the most electronegative element on the periodic table. It's farthest to the right and farthest up. So you can see as we move across the table that electronegativity increases, and as we go down, electronegativity decreases. So to sum it all up, 4 atomic characteristics: atomic radius, ionization energy, electronegativity, and electron affinity. As we go across the table, only atomic radius decreases. All of the other 3 increase. Okay. As we go down the table, only atomic radius increases. The other 3 all decrease. As always, I look forward to seeing you in class. Let me know if you have any questions, and I'll see you soon.